Hello everyone, my name is Stefanos Chaliassos, and today I'm going to present you our study on the characteristics of typing-related bugs in JVM compilers. So, let's start by providing a brief overview of the research on compiler testing. This figure presents the number of publications on compiler testing from 1970 to 2018. We can see that the number of relevant papers on compiler testing has increased significantly since 2011. The year that C. Smith was published. C. Smith is a C program generator that produces programs without undefined behaviors. Testing efforts using C. Smith has found thousands of bugs in C and C++ compilers. Despite the tremendous advances in compiler testing, most of the works have focused on detecting compiler crashes and miscompilations. Those bugs are mainly caused due to issues in the implementation of compiler optimizations. Surprisingly, this growing body of work neglects the testing of compilers' front-end. In statically typed languages with rich and expressive type systems, the implementation of front-ends, and especially the process of static typing, has become particularly complex. This leads to a high density of bugs on components related to static typing. For example, the type checker is the most buggy component on the Scala 2 compiler. Our main goal in this study is to help researchers improve existing compiler validation methods and develop new ones for detecting typing-related bugs. To do so, we empirically studied four main research questions. The first research question is how typing-related bugs manifest themselves. The second one is what are the categories into which we can group typing-related bugs based on their root cause. The third one is about bug fixes and, more specifically, the size of the fixes and the time it takes to fix typing-related bugs. The last one is what are the main characteristics of the bug-revealing test cases. To answer these questions, we examined bugs from the compilers of four mainstream JVM programming languages, namely Java, Scala, Kotlin, and Groovy. Java is one of the most widely used programming languages. Scala is a research product that first appeared in 2004 and unifies the object-oriented paradigm with functional programming. Kotlin is a relatively new language released in 2011 by JetBrains, but it has already become the preferred language for Android development. Finally, Groovy is a hybrid language that supports both dynamic and static typing. Before I dive into the results of our work, let's first understand how we conducted the study. Firstly, to collect the dataset of our typing-related bugs, we gathered fixed bugs related to the typing of algorithms and procedures from the issue trackers of the corresponding compilers. Then, we performed a post-filtering step. In this step, we excluded bugs without an explicit fix and bugs for which we couldn't detect test cases. Our final dataset includes more than 4,000 bugs. Next, our analysis was performed by four researchers in four iterations. In each iteration, two researchers first select a random sample of 80 bugs containing 20 bugs from each language. Then, they manually analyze each bug and categorize them based on our research questions. Finally, two additional researchers validate the categorization in each round. Now, we can answer our research questions. Let's begin with the first research question. What are the main symptoms of typing-related compiler bugs? We have classified bugs into 5 categories. The first category is unexpected compile time error. In this category, the compiler mistakenly rejects a semantically correct program. This category accounts for half of the analyzed bugs. The second most common category is internal compiler error or compiler crash. The third category is unexpected runtime behavior. In this kind of bug, the compiler successfully compiles a source program, but it generates a faulty executable, which in turn may lead to errors in the runtime. Next, a misleading report is when the compiler emits a false warning or a false error message. Finally, a compilation performance issue occurs when a program takes longer than needed to be compiled. For all patterns, we observed similar trends across all compilers. The only exception is the Kotlin compiler, where unexpected runtime behavior is the second most common symptom due to the missing of well-formed checks in the compiler's implementation. Our next research question is, what are the categories into which we can group typing-related bugs based on their root cause? We derived 5 categories that include bugs sharing common root causes, namely type-related bugs, semantic analysis bugs, resolution bugs, bugs related to error handling and reporting, and AST transformation bugs. Type-related bugs occurs when the compiler performs operations related to types. For instance, a type-related bug could happen due to incorrect type inference or incorrect bound computation. Semantic analysis bugs are bugs that arise during the semantic analysis phase of the compiler. Resolution bugs include bugs where the compiler is either unable to resolve an identifier name or the retrieved definition is not derived. Such bugs are usually related to nested scopes, overloading, etc. A bug related to error handling and reporting is when the compiler correctly identifies a program error, but the implementation of handling this error is buggy. Finally, AST transformation bugs is the category where the compiler generates a transformed program that is not equivalent to the original. We observe that the type-related bugs, resolution bugs, and semantic analysis bugs are almost uniformly distributed across studied compilers. On the other hand, bugs related to error handling and reporting are most common in the Java compiler. We also noticed that AST transformation bugs are particularly common in Scala compiler. We attribute this to the fact that Scala is a powerful language, meaning that individual features are often combined together to establish new features and use cases. To better understand bug symptoms and bug causes, let's move on to one example. This Scala program demonstrates a semantic analysis bug related to a missing validation check. Specifically, the program defines two value classes, A and B, with a circular dependency issue as the parameter of A refers to B and the parameter of B refers to A. However, this dependency problem is not detected by the Scala compiler when checking the validity of these declarations. As a result, the compiler crashes at a later stage when it tries to unbox these value classes based on the type of their parameter. This Kotlin example demonstrates a type-related bug resulted in an unexpected compile time error. The program includes a parameterized class named wrapper, which takes one type parameter t and defines a property named value, whose type is given by the type parameter. Later, in line 3, the program creates a list of strings. To convert every element of this list into an object of class wrapper, the code applies the function map by passing a reference to the constructor of class wrapper. Map is a parameterized method in class list whose signature is described in line 4. Specifically, map is instantiated with two type parameters, I and O. Expects as input a function that takes something of type I and returns something of type O. And finally, map itself returns a value of type O. The compiler rejects this program, providing the error message not enough information to infer type variable t. Specifically, map is applied to a list of strings. Thus, the type variable I of the function map is instantiated with a string type, making map expect a function that takes a string as a parameter and returns a value of O. However, there is a bug in the inference engine of the Kotlin compiler which prevents the compiler from instantiating the type variable t defined in class wrapper, and as a result, it is unable to infer the corresponding type for the function reference of the constructor of wrapper. Notably, if we replace the function reference with a lambda, the program compiles successfully. Next, we answer the research question regarding the bug fixes. First, we studied the size of bug fixes and compared them with a previous study on GCC and LLVM bugs that suggest that fixes of compiler bugs are local. We found out that almost 9% of bug fixes contain fewer than 100 lines of code, and 40% are less than 10 lines of code. Furthermore, 60% of the patches updated a single file and only 4% updated more than 5 files. From those results, we can conclude that the fixes are local, which is consistent with the study of Sun et al. Regarding the duration of bugs, we observed that many bugs are challenging to solve. This figure shows the cumulative distribution of bugs through time. According to this figure, half of the investigated bugs were fixed in 1 month, and 15% took more than a year to be fixed. In terms of days to fix, the median is 24 days and the mean is 186 days. We observed that for many bugs, the developers had long-lasting conversations about potential solutions and their implications. This suggests that many typing-related bugs are not fixed immediately after a bug report is opened. Let's move on to our final research question. What are the main characteristics of the bug-revealing test cases? This table displays some general statistics of bug-revealing test cases for typing-related bugs. Most importantly, the test cases are small with 10 lines of code on average. Furthermore, one-third of typing-related bugs occurs when compiling invalid code. This is an important observation because in addition to using valid test cases, identifying typing-related bugs requires passing non-compilable programs as input to the compiler under test. We also categorized the language features included in the test cases into 8 major categories, further divided into subcategories. The 3 more relevant categories are parametric polymorphism, object-oriented features, and type inference. In our paper, we provide more details about those categories and how they are combined in the test cases. Finally, here are the main findings of our study that we hope to help researchers develop techniques for detecting typing-related bugs. Firstly, contrary to optimization bugs, which mainly manifest at runtime as errors, typing-related bugs can potentially affect both compilation and runtime. Consequently, researchers should develop appropriate test oracles that can catch typing-related bugs with a plethora of manifestations. Moreover, typing-related bugs are located in few specific compiler components. These buggy components are typically associated with operations on types, name resolution, semantic analysis, desugaring, or error handling and reporting. A possible direction for researchers is to introduce targeted methods for identifying bugs in these components. Next, typing-related bugs are triggered by non-compilable programs. However, the generation of incorrect programs is a challenging task, as the generated programs must be slightly incorrect. A future research direction could be the proposal of new program generators and mutators that will produce such invalid test cases. As already mentioned, parametric polymorphism is the feature with the most bug-triggering capability. Hence, any future testing effort should focus on parametric polymorphism. Furthermore, the use of the standard library is pervasive in test cases. An interesting direction for stress testing compilers could be the generation of small expressions that use these APIs in a complex manner without requiring the generation of the corresponding definitions. Another observation is that control flow constructs and arithmetic expressions are not common in bug-revealing test cases of typing-related bugs. As a result, current program generators that focus on optimization bugs may not be useful for producing meaningful test cases for typing-related bugs. To summarize, in this work, we empirically study typing-related compiler bugs. We classified them in categories based on their symptoms, root causes, and bug fixes. And finally, we discussed several implications that will hopefully promote the testing of compilers for typing-related bugs. All the data and analysis presented in this study are publicly available on our artifact. Thank you for your attention.